All right, so in the last class, I defined the notions of affine sets, convex sets, and cones. All right, and towards the end of the class, I asked, is every cone convex? Or is it possible to construct a cone which is non-convex? So what do you think the answer is? Yes, did you give any thought to this? If you think of the ice cream cone, is it convex? It is convex, right? If you take a single ray, is this convex? Yes, right? A ray is convex. So, any guesses? Is it possible? So, the claim is yes, you can construct a cone which is non-convex, but can you think of an example? I'm sorry? A hollow cone. Okay, so basically you take the ice cream cone and you remove everything in between, right? That's what you're saying. So firstly, is this a cone? It is a cone, right? You take any point on the surface of the ice cream cone and you scale it up by any non-negative value, it still lies on the surface of this, on the surface, right? So it is indeed a cone and it's not convex, right? So that's an example of a non-convex cone. But in general, if you take any two cones, is the union of two cones also a cone? Which one?
It might lie if you take a right, might lie. And two cones.
Think about it a little more. Yeah? Two rays in different directions. Is this not a cone? So two rays in two different directions, both starting from the origin, mind you. Right? Is this a cone? Take any one point. It lies in one of the rays. Right? If you scale it up by any non-negative value, will it still lie in the union of the two rays? It does. Right. So in fact, any union of cones is also a cone. Okay. But the union need not be convex. So exactly the example that you gave, a union of two rays in different directions, that is an example of a non-convex cone. So not every cone is convex. Okay. So in today's class, I'll give a few more definitions related to convex, affine, and cones, and towards the second half of the class, we'll see an application of a concrete optimization problem, a general optimization problem, and we'll see how we can solve it and how tools from convexity and convex sets can in fact help us in solving such problems. Okay. So very quickly, I'll just go through some definitions which are related to what we've seen so far. So if you recall, an affine set, how did we define an affine set? An affine set is one such that if you take any 2 points, then the straight line that passes through those 2 points is also within the set, right? And so given a particular set which need not be affine, you can think of the smallest affine set that contains this particular set A, right? That's what we'll call the affine hull, right? So the affine hull of any set A is the smallest affine set that contains A. But if you want to think of it from the perspective of how do you generate the affine set, you essentially take it by, you essentially obtain the affine hull by taking all possible linear combinations of the following form. So you take all possible collections of n vectors in the set A, and you look at linear combinations such that the coefficients sum to 1. All right, the coefficients should sum to 1, but they could be positive or negative. There's no restriction. So such linear combinations wherein each coefficient is an arbitrary real value, but all of the coefficients sum to 1, this is called an affine combination. So the affine hull is essentially the set obtained by taking all possible affine combinations of a given set. All right. So very quickly, suppose I take 2 points in say R2, right? What would be the affine hull of this set? Yeah, so if I take A to be, let's say 1, 2, 3, 4, then the affine hull is just the entire straight line that passes through these 2 points. If I take a single point, then what is the affine hull? Just the point itself, right? And if I take 3 points in R2, what would be the affine hull? Sorry? Which is?
Plane.
A plane, but if you're living in R2, then what is the affine hull? R2 itself, right? Of course, that's so in general this is going to be R2, but you have to be a little careful. If the third point lies on the straight line that passes through these two, then that would be just the straight line itself. If it lies anywhere outside the straight line, then it would be the entire R2, right? Okay, that's good. So for any set A, right, any subset of Rn, I can construct the affine hull, which is the smallest affine set that contains A, and we'll say that the dimension of the set is essentially the dimension of the affine hull of A, right? So any affine set, as we've seen, is so every affine set is basically takes what form? Right. So in general, an affine set is some kind of a hyperplane, correct? And I'm using the word hyperplane in a very loose sense, but essentially every affine set can be represented as the solution to some system of linear equations, right? Set of all x such that Ax is equal to B. Right? If you take the set of all x such that Ax is equal to 0, what kind of a set does that define? It's the null space of A, or in other words, it's going to be some vector subspace. And any vector subspace can be written as the solution to a system of linear equations. It can be written as the right null space of some matrix, right? Similarly, any affine set can be written as the solution space of some system of linear equations, right? So it's a little subtle, right? So think about it. It should be fairly clear that any set of solutions to, or the solution space of any set of linear equations is an affine set. But what takes a little bit of work is to show that every affine set can be represented in this particular form. Okay.
But the coefficients also to be sum up to 1.
I'm sorry?
Coefficients.
The coefficients should sum up to 1. Yes. But then the coefficients could be arbitrary real values. Right? So in R3, the only kind of affine sets that you can have are either points, of course there's the null set, or a point, a straight line, or a plane, or the entire R3 itself, right? And all of these can be thought of as either subspaces or shifts of subspaces. So that's all the kind of affine sets that you can generate. Okay? And the dimension of a particular set, an arbitrary set, is the dimension of this affine subspace. Right? So, for instance, if I take a circle, right, a circle in R3, what would be the affine hull, or what would be the dimension of this circle? Basically, you take an infinitesimally thin ring, right, in R3. Right, you think about this. What would be the affine hull of this ring in R3?
Ring of freedom.
So you think of it as an infinitesimally thin ring, right? That would just, the affine hull would just be the plane that contains the ring, right? So what would be the dimension of this ring? 2, right? Because the affine hull is a plane in 3 dimensions, correct? So if you take any 3 points in R3, what would be the dimension of this set containing 3 points? 2 could be 1 also, right? Because if those 3 points lie on a straight line, then the affine hull would just basically be a straight line, and therefore the dimension would be 1. But if they're not collinear, if they don't lie on a straight line, then basically the affine dimension would be, or the dimension would be 3. And if you take 4 points, yeah, it could be 1, it could be 2, it could be 3. Right. Okay. Good. Now, just as we defined the affine hull, we can also define this notion of a convex hull, which is the smallest convex set that contains A. Right? And how do you generate the convex hull? You take all possible convex combinations of points in the set A. So what is a convex combination? It's any linear combination such that all of the coefficients are greater than or equal to 0 and they sum to 1. Now, if I take any 2 points in R2 or R3, what would be the convex hull of these 2 points? It would just be the line segment that joins these 2 points, right? That would be the convex hull of these 2 points. Remember, what is a convex set? A convex set is basically a set where if you take any 2 points, then the line segment joining those 2 should also lie within the set. So obviously, if you take these 2 points, which are the only 2 points in A, then the entire line segment that joins these 2 should also be in the convex hull of A. And you don't need anything else. And now if I take a third point, what would be the convex hull of these 3 points? Yeah, triangle, right? It would be, I mean, the entire triangular region that is enclosed by these 3 points. Right? Obviously, because since these 2 points belong to A, the straight line joining these 2 should be in the convex hull. Since these 2 points belong to A, the straight line joining these 2 should be in the convex hull. And similarly, since this entire line, since these 3 lines belong to the convex hull, if you take any 2 points, say this and this, then the straight line joining these 2 should also be within the convex hull, and so on. As we define the convex hull, we can also define the conic hull, which is, again, you generate the conic hull by taking so-called conic combinations. So linear combinations where all of the coefficients are non-negative. Okay. So this is the conic combination. The set of all possible conic combinations of points in A gives you the conic hull of A. Now, unlike the other two, where the convex hull was the smallest convex hull smallest convex set that contains A, and affine hull was the smallest affine set that contains A, the conic hull is the smallest convex cone that contains A. Just a matter of definition. Right. So if I take just a single point in let's say R2, right, I'm just going to look at it visually. So suppose I take 2 points, let's take a single point, then what is the conic hull of this set A? The set is just a singleton. It has to be a cone. Yeah. So it is the ray that starts from the origin and passes through this particular point. Right. So this would be the conic hull of the set A. Now if I take 2 points in R2, let me take another point. What would be the conic hull of these two? Yeah? Exactly. So obviously the conic hull should contain this ray as well. But remember, it's the smallest convex cone that contains A. So this would essentially contain this entire region that is enclosed, that is between these two rays. So that would be, so if this is my x1 and this is my x2, then this set is basically the conic hull of x1 comma x2. Okay, great. So just as a simple exercise, try to find the affine hull, the convex hull, and the conic hull of these two sets. Okay. Try to also plot what you get, but also try to get an analytical expression for these three sets. Okay. Okay, anyway, this is in the notes. Okay. A special kind of an affine set is a hyperplane, which I'll define as the set of all x in Rn such that A transpose x equal to B.
Does the conic hull always have to be
Yes.
by definition?
By definition, yes. I mean, okay, it's a simple exercise to see that if the conic hull is closed under all possible conic combinations, then it's also closed under convex combinations. Because a convex combination is a restriction of conic combinations.
To create a set containing A, which is cone,
Yes.
that wouldn't be called a cone.
That is not, I'm not going to call that the conic hull. So,
Is statistically convex. Something hull is smallest cone that contains.
correct. That is not called the conic hull.
But then that is definable.
You can define it, sure, of course. You can always define it. So, for this particular example, the smallest cone that contains x1 and x2 would just be the union of these two rays. Right? But the reason why I don't call it the conic hull is because I want it to be closed under these conic combinations. This is a very specific reason to do so. All right.
How do you prove that the other sets are the smallest possible?
You mean to say why this is the smallest convex set?
Convex and
It's a little more, it requires a little bit of analysis, but again, you can sort of convince yourself intuitively.
yeah, intuitively it makes sense.
Correct. Mathematically, yes, it requires a little bit of effort. But yeah, for now, just believe me that this is the smallest convex set that contains A, and this would be the smallest affine set that contains A. That's also because you're looking at all possible affine combinations of all possible collections of finite elements in finite set subsets of A. All right. Coming back, so a hyperplane defined by a vector A and a number B is basically the set of all x such that A transpose x is equal to B. Okay. So it's a special affine set. And what is the dimension of this particular affine set? Yeah. Is it n? It's going to be n minus 1. Right? So firstly, this is an affine set. We're convinced by that. Okay. And this is the right null space of, or you take B equal to 0, just to be concrete. If you take B equal to 0, then this is the right null space of a matrix of what rank? 1, assuming of course that A is non-zero. So we're assuming that A is non-zero. So it's the right null space of a rank 1 matrix. So what should be the dimension of the subspace? It's n minus 1. So this is my A. The dimension of A is n minus 1. I'm sorry?
When B is 0.
When B is 0, it's a subspace, and therefore that is a dimension. But recall that I defined the dimension of an arbitrary set, which is the dimension of the affine hull of A. Right? Okay. And how do you define the dimension of the affine hull? So this, you can view the affine hull or any affine set as the shift of a subspace. Correct? So for example, in R3, you take a plane in R3. What is the dimension of the plane in R3? It's 2. Right? Because it's the shift of a 2-dimensional subspace. Correct? Similarly, a line in R3, the dimension is 1 because you can view it as the shift of a 1-dimensional set or of a 1-dimensional subspace of R3. Right? Similarly, you can obtain the hyperplane as the shift of an n minus 1 dimensional subspace of Rn. Right? So the dimension of a hyperplane is n minus 1. Any questions? Okay, if you want to be, let me be a little more precise. So how do we define the dimension of an affine set? Okay. So first, I want you to show that any affine set A, which is a subset of say Rn, can be written as the set of all x in Rn, which is the solution space of some system of linear equations. Okay, this representation need not be unique, okay, but nevertheless it can always be written in this particular form, so that every affine set can be written in this particular form. Okay, now if you can write this in this particular form, then the dimension of A, you can define this simply as the nullity of A, of the matrix A. Okay, so this is a concrete definition of any affine set. So now if you are given an arbitrary set A, you can look at the affine hull, and so the dimension of the affine hull is defined to be the dimension of the set A. Okay. All right. So in 3 dimensions, if I think of a plane, right? So so in 3 dimensions, a plane is the only hyperplane that you have, right? And this hyperplane splits the entire R3 into 2 parts, right? So each of these parts is going to be called a half space. So a half space is basically set of all x in Rn such that A transpose x is greater than or equal to B. Yeah.
Dimension of affine set.
So first I want to define the dimension of an affine set. If I can define the dimension of an affine set, I can define the dimension of any set just by looking at the affine hull of that set. Correct? So how do I define the dimension of an affine set? My claim is that every affine set can be written as the solution space of a system of linear equations, right? Now this representation may not be unique. I could find different A and B for which A, this set A can be written in this particular form. But no matter which representation I choose, the nullity of A will always remain the same. That is going to be unique, and that is what I will call the dimension of that affine set A. Correct. So this is the nullity of the matrix A, or if you want me, if there's any sort of confusion, let me call this C. Right. So this is the set A. Okay. Any questions? All right. So we now know what a hyperplane is, what a half space is. So given any hyperplane, it defines 2 different half spaces. One is the set of all x such that A transpose x is greater than or equal to B. The other is the set of all x such that A transpose x is less than or equal to B. So these 2 sets intersect on the hyperplane. But I can write it in this general form because this is the same as saying minus A transpose x is greater than or equal to minus B. Right? Okay. So if you think about it, let's take R2. Let me take R2 and I define some hyperplane. Then corresponding to the hyperplane, there are two half spaces. Now I can look at multiple such half spaces and take an intersection of these half spaces. Right, I can take the intersection of multiple half spaces. So any intersection of finitely many half spaces is a polyhedron. Finitely many is important. But one thing to note is that so even a single half space by definition is also a polyhedron. The polyhedron need not be bounded. The single half space is a polyhedron. What about the first quadrant in say R2? That is a polyhedron because you can write this as the first quadrant can be written as an intersection of the set of all x1, x2 such that x1 greater than or equal to 0. So this is one half space, set of all x1, x2 such that x2 greater than or equal to 0. Right? Or in other words, this is one 0 x1 x2 greater than or equal to 0. This is 0 1 x1 x2 greater than or equal to 0. Right? So in this case the a vector is 1 comma 0 and in this case the a vector is 0 comma 1. Right? Now if the polyhedron is also bounded, it's called a polytope. Again, this is the terminology that we will use. But one thing to note is that this terminology regarding polyhedron and polytope, it's not consistent. There are some books, some papers which say that bounded so if it is bounded, then it's called a polyhedron, and general polyhedrons are sometimes referred to as polytopes, and vice versa. So some references don't distinguish between polyhedron and polytope, and sometimes they use the exact opposite definition, right? But for us, we'll follow the book by Boyd and Vandenberg, where they say that a polyhedron is any intersection of finitely many half spaces, and if it is bounded, only then is it going to be called a polytope. So a polyhedron is a more general term. So every polytope is a polyhedron, but not the other way around. Right. Any questions so far? Okay, so now let's look at a very specific optimization problem. So it's a general problem called maximum weight perfect matching in a bipartite graph. So what is a bipartite graph? It is just a graph containing two sets of vertices. So the vertices on the left are going to be called the left vertices. The vertices on the other side are going to be called right vertices. And we'll assume that all of the vertices, all of the left vertices are connected to all of the right vertices. But there's no connection between vertices on the left, and there's no connection among vertices to the right. Okay? So every left vertex is connected to some right vertex, and every right vertex is only connected to some left vertex. So that's called a bipartite graph, and this is what is going to be called a complete bipartite graph. That is, every left vertex is connected to every right vertex, and vice versa. Okay. So let's take perhaps a motivating example to say what is a maximum weight perfect matching. Suppose that you have three items that you want to sell. Okay, let me call it item 1, item 2, and item 3. And there are three buyers, exactly the same number of buyers. So buyer 1, buyer 2, and buyer 3. For whatever restrictions, you only want to give one item to each buyer. A buyer can't buy more than one item. But the thing is, the price of the item is not fixed. You don't set the price of each item, but each buyer is going to say how much he or she is willing to pay for each item. Okay, so maybe buyer 1 is willing to pay whatever 0.2 units for item 1, say, I don't know, $0.2 for item 1, $1 for item 2, and $2 for item 3, and so on. Right. Now this is given to you. You know which buyer is willing to pay how much for each item. Your goal is to just maximize you want to maximize your income. So how do you allocate items to buyers such that the total amount of money that you get is the maximum? All right. So you want each BI to get exactly one item, and you also want to maximize your revenue. The amount of money that you get. Okay. Now this is one example, but a lot of problems can be posed as a similar problem. So for example, if you want to take let's say communications, right? Now these buyers could be different users, and these items could be specific channels or frequencies that they can connect to, and maybe for each user they see a different data rate depending on which frequency they connect to, and each user can be connect to only one frequency, and you want to maximize the total throughput. You want to make sure that there is maximum utilization among all frequencies. So perhaps you want to maximize the total data rate that you can support in this system, right? And so on. There are multiple such examples. So this is a very general formulation, correct? So formally, what is a maximum weight perfect matching? So you are given this matrix W of weights. So the matrix W of weights could be the amount each buyer is willing to pay for each item. Okay. So W is an n by n matrix of weights. So right now we are assuming that this is the number of left vertices is exactly equal to the number of right vertices. Although these notions of matchings can be generalized to, in fact, not just bipartite graph, arbitrary graphs. But for now, we'll just focus on the special case where number of left vertices is equal to number of right vertices. Okay. So W is an n by n matrix of weights. The goal is, so this matrix of weights can be represented as weights on the edges of this particular bipartite graph. Okay. So in this context, for a given bipartite graph, a matching or a perfect matching is a subset of edges such that each vertex has exactly one neighbor. All right. So that is what it is in graph theoretic terms. In this particular example, it's basically an allocation. So let's say that I say that item 1 goes to buyer 1, item 2 goes to buyer 2, and item 3 goes to buyer 3. That corresponds to one perfect matching. Okay. Another perfect matching could be item 1 goes to buyer 3, item 2 goes to buyer 2, and item 3 goes to buyer 1. Now, what is the weight of each matching? It's basically the sum of the weights of the edges in that particular matching. Weight of a matching is just sum of the edge weights. So for example, let me take this case. So suppose I decide to allocate user item 2 to user 3. And maybe item 3 to user 2 or buyer 2, and item 1 to buyer 1. This is one particular perfect matching. Another perfect matching is maybe I decide to allot, so user 1 gets or buyer 1 gets item 2, a buyer, and buyer 2 gets item 1 perhaps, and buyer 3 gets item 3. Right, so both of these are examples of perfect matchings. What is the weight of the first matching? It is just 0.2 plus 1 plus 1.2, which is 2.4. Right? What is the weight of this perfect matching? I guess this is, 1. So it is 7 plus 3 plus 1. That's 11, right? So obviously the second perfect matching is better than the first perfect matching because it gives me a higher weight. My goal is to choose a perfect matching which maximizes the weight. Okay? Because again, if I think of the problem, if I think of this particular problem, I want to maximize the amount of money I can make. Right? So the goal is to find the max weight perfect matching. Okay, the problem is clear. Fine. Now, what is a brute force approach to solving this perfect matching? Yeah, so you basically look at all possible perfect matchings. How many perfect matchings can you have? There are n factorial perfect matchings. In fact, if you think about it a little, a perfect matching just corresponds to a permutation, right? Corresponds to a permutation. Let's call it sigma, right? So sigma is basically a bijective map from n to n. This notation, square brackets n, is nothing but just 1, 2, 3 up to n. Right? Now, in this particular notation, what would be the weight of the matching sigma in terms of the Wij's? So basically, sigma of I essentially tells you what I gets mapped to, or which edge or which vertex on the right. So the ith vertex on the left is connected to the sigma ith vertex on the right. So it is summation I equal to 1 to n. Okay, Wi comma sigma of I, right? Very good. So this is the weight of a particular matching or a particular permutation. And the brute force approach is basically you just look at all possible matchings and then try to find the one with the largest weight. Can you think of any other approach that is better? Which is?
Take the maximum.
Okay.
Like column root itself.
Okay.
The remaining max.
Okay. Is it going to be any less than n factorial?
Yeah.
Okay. So basically, initially you look at n, right?
N square.
Correct.
So it will be maximum.
Okay.
Now we delete the one column. Now we have n minus 1 n minus 1. And you again search for the goods. And square into n minus 1. But it's for the
Um. I'm sorry. So you're looking at what?
We take the maximum.
The maximum weight in the entire matrix.
Yeah. So now that buyer and that item gets.
But how do you know that gives you the best perfect matching?
Okay, I wouldn't give you the best.
Okay.
An approximation.
Fine. So you're not guaranteed to get the maximum weight matching using that particular approach. Correct?
Yeah.
Okay, fine. But yeah,
So suppose you have three cross.
yes.
Now what I'll do is this method only, but
Okay.
it means that last this third column is everything going to the third item.
Item.
Third
Okay.
item.
Okay.
So only one thing in the third thing can be like on this.
Okay. Basically, what we're both suggesting are potentially suboptimal algorithms, right? They're not going to give you the optimal solution. I want the optimal solution.
Start with a random permutation. Go see if it gets better. If it gets better.
Okay. It's doubtful that you will do any better in terms of
Or
computation.
else take the 3 cross 3, arrange it in a line. Take the maximum weight.
So again, the maximum weight perfect matching need not have the largest weight. So it could be possible that there is some perfect matching for which the sum of the weights is large, but it does not include the largest weight. Okay. So for example, in this case, let's take a, sure if I can do it for a 2 by 2. Yeah, let's take a 2 by 2 case itself, where it will be easier to see. So let's say that this is 10 and this is 1 and these two are 8. So what is the maximum weight perfect matching? Or what is the weight of the maximum weight perfect matching? 16. But what is the largest weight? 10. Right? So 10 is never included in the maximum weight perfect matching. So the greedy approach could do very badly in principle. Right? In principle, I could just have had this, say, 9 and 9. Correct? So potentially you could do badly. So this is an example of a combinatorial optimization problem. So what is your search space? It is the set of all permutations, right? Which is a combinatorial object. It's a discrete object. There are only finitely many. But for large n, the computational complexity is actually very, very large. Okay. So first let's just write a program to find the maximum weight perfect matching and see how it does. Let's just use the brute force approach. Okay. So what I'll do is I will generate a random weight matrix. Let's fix some n. I'll start with n equal to 5. Okay. N comma n. So whatever, it's just a bunch of numbers, but perhaps it's easier to visualize in this particular form. So the more yellow it is, it means that the weight is large. The more blue it is, that means that the weight is small. So for example, this would correspond to 0.985. This corresponds to 0.186. Okay. And now let's try to cycle through all possible permutations and find the maximum weight matching. So let's define, so max weight, I'll set this to be equal to 0. Max weight matching is n for So this is just something that allows me to cycle through all possible permutations. Let's say that the weight zero. So the total weight is just W of I comma j. So this circles through all I comma j's in the matching and adds it up. So if the weight is greater than the max weight, then you set max weight equal to weight and max weight matching is right. So in this case, it gives me thing, right, and perhaps let's see a smaller example where we can guess what the correct weights are. Okay. So in this case, what is the maximum weight matching? Yeah. So it should be 1 should get mapped to 2 and 2 should get mapped to 1, right? So the maximum weight should be 0.97 plus 0.42. Okay, and that's correct. So basically the indices start from 0. So 0 gets mapped to 1 and 1 gets mapped to 0. And the max weight is 1.4, right, as expected. Now I take n equal to, say, 10. So it's a 10 by 10 matrix. A lot of entries, hard to guess what the correct answer should be. But now if I try to run this, take some time. And this is just for a 10 by 10 matrix. Right? Okay, so it took 11 seconds to complete this. So obviously this is just for 10 items and 10 buyers. Now suppose I have, let's say, 1,000 items and 1,000 buyers. Can I do it? No. This greedy of this brute force approach is really, really bad. Right? So the question is there a way to solve this efficiently? Is there a way to find the maximum weight matching in time that is very, very fast? The answer is yes. So there's something special about the maximum weight perfect matching for bipartite graphs.
We can solve it by we introduce the nth one. We only have to check n swaps.
Not really. So we'll use a completely different approach, right? So whatever you're suggesting is a very combinatorial approach. I am not going to solve this combinatorial optimization. In fact, I'll pose this as in fact, so this is a discrete optimization problem, right? I'm going to formulate it as a continuous variable optimization problem. And then solve that continuous variable optimization problem. Okay, so that's what is typically called a relaxation. You're given an optimization problem, you relax some of the constraints so that hopefully you can solve it efficiently, and see how the solution to this relaxed problem compares to the original problem itself. Okay?
Let's give you the exact same.
I'll come to that, just wait a little bit. Okay. But first, it depends on how I relax it. All right. So I look in general, the answer is no. The relaxed problem, you could, if you don't do the relaxation properly, then you will not get the same solution as what you hoped for. And sometimes some relaxations could perform very badly. Right. But this is an example of a problem where there is a good relaxation. I'll say what that good relaxation is. So I'll formulate this problem in a slightly different way. So the variable, the same problem, okay, I'm not making any relaxation. So the same problem, I'm going to formulate it as the following. So my variables is going to be an n by n matrix X. N by n matrix with zeros and ones. Okay. The 0, 1 matrix basically tells me the connectivity structure of the matching. Okay. Essentially, you can think of it as the adjacency matrix that corresponds to the matching, if you're familiar with the term. But anyway, in terms of X, suppose that the X corresponds to the matching. So there's a 1 if it corresponds, if I is connected. So Xij is 1 if I is connected to J and 0 otherwise. Then what is the objective function? What is the weight of that particular matching? It would simply be summation I over all possible I and j, wij, xij. Only if X corresponds to a perfect match. Okay. So basically, if Xij is 1 if sigma of I equal to j and 0 else, right, then this is exactly equal to this particular quantity. Correct? You're convinced of that? If I take Xij is equal to this. Right? Fine. So now what are my constraints? I want to impose the constraints that X should correspond to a permutation matrix. Correct? Which is what? So I want, how many ones can I have in each row? You look at each row of a permutation matrix, how many ones can it have? Exactly 1, right? So summation overall j xij should be equal to 1 for all I. Similarly, how many ones can I have in each column? Exactly 1 for all j. And for it to be a permutation matrix, X or Xij should be either 0 or 1. Right? I can't have any other restriction. Which one? I know. I mean, this is sort of aside. I mean, that is true. Basically, I am saying the same thing in this particular form. That's all. And I'm doing it for a very specific reason. Okay. So you agree that this particular problem, right, is the problem that we want to solve. So if I can solve this efficiently, then I basically solved the maximum weight perfect matching problem. Okay. Hopefully you all agree with me on this. Okay. So now what I'm going to do is I'm going to define a new problem which has exactly the same objective function, The first constraint is exactly the same. The second set of constraints is exactly the same, but I'm going to relax the third constraint. I'm going to say that the only restriction I want is xij should be greater than or equal to 0 for all I comma j. Okay, so this is a continuous variable optimization problem. Right? Now, if you think about it a little bit, what kind of a function is this objective function in terms of x? It's a linear function, correct? And what about the constraints? So these constraints are, of course, linear. Right? Even this is, plus there's an additional non-negativity constraint. Right? So this is in general such an optimization problem is called a linear programming problem, because the objective function is linear and the constraints are also linear. So this is what I'll call the LP relaxation, or linear programming relaxation of my problem. Okay, so now it's a new problem. Right? It's not guaranteed that this solution corresponds to this particular solution, but it'll give me some solution nevertheless. The main point is that you can solve a linear program very efficiently. Okay. So what I'll do is basically use a standard solver to solve this, and I'll also take this opportunity to introduce a Python library called CVXPy. Okay, we'll be using this to solve many convex optimization problems. Okay. A link for CVXPy is already there in the course webpage, so go through it. There are a lot of examples, a lot of problems solved that have been solved over there, and it's fairly simple. There's not too much of a difficulty. It is exactly how you would. It's a very natural way to program, and you can find solutions to problems in using just a few lines of code, provided, of course, that you are able to formulate the problem carefully enough. Okay, so in order to be able to use CVXPy, the problem should be a convex optimization problem, and you should be able to represent it in a nice enough form. If you're able to do that, then you can solve it efficiently. And it's very natural. Basically, you define your variables, you define your constraint, you define your optimization problem, and then solve. That's it. Just 4 or 5 lines of code. So I'll first define my variable, and you'll see that it's a very natural. So to define a variable, I just use CVXPy. So I've imported CVXPy as CP. So cp.variable, I want an n by n matrix, so it's just going to be n comma n. Right now I'll define the constraints. The constraints are going to be in the form of an array. Each constraint is separated by a comma, right? So in this case, I want the entries of x to be greater than or equal to 0, right? And if I sum the entries of a particular row, it should be equal to 1. If I sum the entries of a column, it should be equal to 1. Those are the constraints that I have. So the sum of the entries of x along a particular axis, this should be equal to 1. And sum of the entries of x equal to 0, this should be equal to 1. So here I've just defined a variable which is an n by n matrix. My constraints are just entries should be non-negative. Each row column comes to 1. So this should be access equal to 1. Okay, so these are my constraints. What is my objective? So the objective is always either to maximize something or minimize something. In this case, I want to maximize, right? So basically, I take the product of x and w and then sum all of the entries of this product. Right? So it is cp dot multiply x comma w, and then I sum I think it only sums the columns, so let me just do this. So I have my variables, I have my constraints, I have the objective. Okay. It's up to me to verify that this is a convex optimization problem. And this is a convex optimization problem as it so happens. And now I just say so now it is cp dot problem of objective constraints. So I've defined the problem. That's it. Okay, just these many lines of code and I get the solution. Let me say that the maximum weight that I get using the linear program, and let me print and let me also print the solution. Or LP solution. Okay, it's something huge, but then I get, it took me almost no time to solve. But what about the maximum weight that I got using the LP? Okay, forget about the last few digits, but at least up to the first 4-5 digits after the decimal point, it's exactly the same, right? And it's a fraction of the time that my brute force approach took. But I can also try to plot the solution itself, right? So right now in this case, I wanted X to be a 0-1 matrix. But using my linear program, I don't know whether I'm going to get a 0-1 matrix or not. Potentially, I could get a matrix with values between 0 and 1. Correct? So let's see if that happens. So as it turns out, no. I am getting, well, of course, there are so some of these values could be close to 0 or close to 1, but if I just use a simple thresholding, then I get a nice permutation matrix. This was for one particular case, right? Will it work all the time? So let me just generate something else. In fact, let's take 50 by 50 matrix. Okay, this is what the weight matrix looks like. It's a huge matrix. There is no hope of solving this using the brute force approach, right? So I'm not going to try to solve it using the brute force approach, but boom, I just get the solution, right? Again, almost no time, 50 by 50 matrix. Zero one matrix, right? And you can, in fact, you can see that this will actually be a permutation matrix. Okay, let's see, 200. All right, huge matrix, right? .6 seconds. That's all that it took. Again, what you will get, if you can verify that this is also going to be a permutation matrix. So what is happening? Why is this? I made a relaxation, right? I changed one of the constraints to be a continuous variable optimization problem. But still, in the end, what I'm getting is the solution that I was looking for, right? So this uses a couple of properties. So firstly, one property is that I can solve a linear programming problem exactly. There's an efficient solver to solve a linear programming problem, any linear programming problem. Okay? And the complexity essentially depends on the number of constraints that I have, and yeah, it's related to just the number of constraints and the number of variables that are in it. It's polynomial in those. Okay? The second property is, as it turns out, for this special problem, the LP the solution to the linear programming relaxation happens to be the solution to this optimization problem itself. Okay. Correct. How we can guarantee, or why is it that this phenomena is happening, that the solution to this linear program is the solution to this particular optimization problem? So again, I'm just going to state some facts. I'm not going to be able to prove all of it, but
that if we imagine the problem as product can be shared between the people, and each person should get a full product. That's what you're replacing it to.
yeah, but again, that'd be sort of very special. But here there are some more general phenomena that I want to bring out. Okay, so firstly, as it turns out, so this is a rather intuitive fact. So I'm just going to state these as facts. I will not prove all of these. The first fact is that the solution, okay, so first let's think about the constraint set. What is the geometry of this particular constraint set? In this case and in general for any linear program. Convex, but it's related to the topics that we saw earlier in this class itself. So you look at just one of these constraints. Okay, what does one constraint look like? What kind of a set does it define? It's affine, sure, but just look at one of these. Summation overall j xij equal to 1. What set does that define? For a given I. It is convex, yes, but it's a special set. What form does it have? Convex hull of what? Again, it's just the set of all x, right? So set of all x such that let's say summation overall j x1j is equal to 1. Yeah, it's a hyperplane, right? So this just defines a hyperplane. If I said that this is greater than or equal to 1, what would this define? Half space. So if I also set the constraint that it should be less than, or this is greater than or equal to 1 and less than or equal to 1, then that would give me the hyperplane, right? So the constraint set is obtained by imposing each of these linear constraints, correct? So what is the intersection? So basically the constraint set is the intersection of each of these constraint sets, correct? That's what it is. What does that define? What kind of an object is it? Yeah, it's a polyhedron, right? So you take any linear program where each constraint is linear. So each linear constraint defines a half space, and therefore you have finitely many linear constraints. So in the end, the constraint set is just going to be a polyhedron. So the constraint set of any linear program is a polyhedron. That you can see, that's, you can prove that exactly. Right? And in this particular case, what more can you say? Is it bounded? Can any of the xij's, so if you take any x that satisfies all of these constraints, can any xij be greater than 1? No, right? So in fact, the constraint set is bounded. Therefore, the constraint set is in fact a polytope, correct? The second fact is that if the constraint set is a polytope, then the solution of the linear program can be chosen to be a vertex of the polytope. Okay. Again, I won't prove this, but you can think about it intuitively. So let's think about it in 3 dimensions, right? Now in 3 dimensions, suppose that my constraint set, or suppose I have 2 variables. I have 2 variables, and on the z-axis I have the function value on those 2 variables. I have a bunch of constraints, right? My set of constraints gives me some polytope, which is going to be some polygon, right? So this is basically my constraint set. Now if I think about it, the function value is the objective function is a linear function. So there is some direction along which the function value keeps increasing, right? With the gradient. So basically I can look in the direction of the gradient. What is the gradient going to be at any point? It's going to be a fixed vector, right? And the gradient is the same at all points, right? So my f of x is some A transpose x plus b potentially, correct? What is the gradient of f of x? It is A at every point x, right? So in other words, there is some direction along which, so I look at the direction along which the function value increases the most. That is the direction of the gradient. So take any point, I take any point within this constraint set. I keep moving in the direction of the gradient. It's always the same. It's always one direction, correct? Again, this is something that requires you to think about a little bit. You keep moving in any direction, you will hit an edge, correct? So either the edge can be perpendicular to the direction of the gradient, or it could be slightly at an angle. If it is at an angle, then you can move further. So the function value keeps increasing until you hit a vertex. Right? So let's assume that this is my constraint set, and the direction of the gradient is this direction. Okay? So in other words, from any point, if I move along this direction, then the function value keeps increasing. Where do you think the maximum is achieved within this constraint set? It will be at this vertex. This vertex will be the point for which the function value is the maximum. Now let us say that the gradient is in this direction. Then where would the function value? Yeah, so it's basically, maybe I didn't draw it well enough, but let's say that this is the direction. Then this point would be where the function value is maximum. Now suppose that the gradient is kind of perpendicular to one of these edges. Then again, any point on this edge will achieve the maximum function value, right? But then I can choose any vertex along this edge to be a point of maximum. So no matter what happens, the solution to the linear program can always be chosen to be one of these vertices of the polytope. Okay? Correct. So again, I'm not formally defined what a vertex is of the polytope, right? But you can think about it intuitively in at least 2 and 3 dimensions, right? So it is going to be in the constraint set, right? And it's going to be one of these points.
You're saying linear programming itself,
Correct. So take any linear program, as long as your constraint set is bounded, the solution will always be, of course, either it could be an edge potentially, but in general, it's going to be a vertex. There will be one vertex which achieves the maximum function value. Okay? That's a special property of a linear program. That's one thing. That's the third fact that you need, that in this case, all the vertices of this particular constraint set happen to be permutation matrices.
That's like solving previous problem.
Exactly. So the solution of your linear program is going to be the solution to the original problem. Can solve this efficiently because there are, yeah, you can think of gradient based methods, but there are better methods for linear programs. There are very efficient solvers for linear programs specifically. Right? So the third fact is that the vertices of this particular constraint set happens to be equal to set of permutation matrices. So the constraint set, if you think about it, so this is the set of all matrices with non-negative entries, and each row and each column sums to 1. So these are what are called doubly stochastic matrices. All right, and there is a very nice result called, just for your information, the Birkhoff von Neumann theorem. Which basically says this, that the set of vertices of doubly stochastic matrices is equal to the set of all n by n permutation matrices. So for this combinatorial optimization problem, right, I can solve this by just a simple linear programming relaxation. As it turns out, the computational complexity is just linear in n for this particular case, for this particular linear program. Whereas the brute force combinatorial approach would require n factorial complexity. I'm sorry, I think it's quadratic in n. So it's linear in the number of variables, which is the number of variables is n squared. Right? So this, in this case, it's just quadratic in n. So that's very efficient. I'm just saying that it is true. In general, for a linear program, it's a little nuanced to say what the computational complexity is. But in many cases, it is linear in the number of variables and constraints. Which one? The second is that if it is a polytope, then the solution of the linear program is always a vertex. And for this case, the vertex is going to be a permutation. So the linear programming relaxation gives me the solution to the original problem. Okay, so let's stop here. Any other questions?